This is Advent of Code, day 10 in OCaml, starting in 3, 2, 1, go. Cathode-Ray tube. You avoid the ropes, plunge into the river, and swim to shore. The elves yell something about meeting back up with them upriver, but the river is too loud to tell exactly what they're saying. They finish crossing the bridge and disappear from view. Situations like this must be why the elves prioritize getting the communication system on your handheld device working, and you pull it out of the pack. The amount of water slowly draining from a big crack in its screen tells you it probably won't be of much immediate use, unless, that is, you can design a replacement for the device's video system. It seems to be some kind of cathode ray tube screen and simple CPU that are both driven by a precise clock circuit. The clock circuit ticks at a constant rate. Each tick is called a cycle. Oh no. Start by figuring out the signal being sent by the CPU. The CPU has a single register X, which starts with the value 1. It supports only 2 instructions. Add X V takes 2 cycles to complete. After 2 cycles, the X register is increased by the value V. V can be negative. No op takes 1 cycle to complete. It has no other effect. CPU uses these instructions in a program to somehow tell the screen what to draw. Add x3, add x negative 5. At the start of the first cycle, during the start of the second cycle, third cycle x is still 1. After the third cycle, the add x3 instruction and finishes execution setting x to 4. At the start of the fourth cycle, add x negative 5 instruction begins during execution. Maybe you can learn something by looking at the value of the X register throughout the execution. For now, consider the signal strength, the cycle number multiplied by the value of the X register during the 20th cycle and every 40 cycles after that. Okay. So we have 420, 11 for 20th cycle. Starts with 1 during the 20th cycle. Okay. Parse input. Module instruction. Type T equals no op or add x of int. Deriving okay. If s equals no op, then else add x of insta add x d. Okay, how do I want to do this? X, exp this dot take does that work? Yes. Nope, 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 nope. Cool, working. Okay, let's do module CRT CPU T equals mutable current what is it? Instruction pointer. Index. X. Let create equals insters do I want all this stuff? Remaining cycles. Remaining cycles. At the start of the first cycle. Insters inster index equals 0. List dot to array. Mean cycles 0. X equals 1. Okay. Let CPU equals CRT CPU dot create insters in let key cycles equals 20, 60, 20 up to 220. No, 2060. And yep. Happy New Year. And let part 1 equals 0 in and then how do I do this? List dot range 0 5. List dot iter eventually cycle let's see, let tick t equals okay. Let okay, how should I do this? During the 20th cycle. What made me try OCaml? Only people who use OCaml are people in love with functional programming or those that work at like Jane Street. I'm in one of those two camps and not the first camp. Okay, so how do I set up this first tick? Or do I just have the cycle number be 1? Okay. If list.mem Yes, I live in New York now. List.mem key cycles cycle list.mem equal int dot equal. Then part 1, I'm doing the sum equals part 1 plus CPU dot x. CRT CPU dot tick CPU. And then let's probably just go a couple extra just in case. Okay, so when we tick, we let's just call this next instruction index. No. If remaining cycles equals 0, let cycles per op let cycles equals function. How do I want to do this? Ooh, okay. What if I did this? Init. No, I'm not going to make this more complicated. Okay, so when we tick, oh, okay, I can do this. Equals inst.cycles list.head xn insters. Okay, so remaining cycles. T remaining cycles, minus 1. If the remaining cycles is 0, then let op equals t.insters inster index let apply inster t equals match inster with no op, then do nothing, add x, d delta, then t dot x delta. Apply inster t then so we apply the instruction, or complete instruction. Complete instruction, and then we set inster t inster index plus 1 t dot remaining cycles inst dot cycles insters dot t dot insters That's not unused. Okay. There we go. List.mem oh, there we go. Oh. 103. Oh, okay. Cycle times. That seems more like it. Woohoo! Seems like the X register controls the horizontal position of a sprite. Specifically, the sprite is 3 pixels wide, and the X register sets the horizontal position of the middle of that sprite. In this system, there is no such thing as vertical position. If the sprite's horizontal position puts its pixels where the CRT is currently drawing, then those pixels will be drawn. You count the pixels on the CRT, 40 wide by 6 high. The CRT draws the top row of pixels left to right, then the row below that, and so on. The leftmost pixel in each row is in position 0, rightmost pixel is in position 39. CRT draws a single pixel during each cycle, representing each pixel of the screen as a £. Here, the cycles during which the first and last pixel are drawn. Okay. Whoa. Okay. So now we have let part 2 equal equals ref A, B, A, B, C, string.car list. ABC. Append. Part 2 cars equals in if cycle (23) mod 5 6. Okay. Then part 2 cars equals part 2 cars. So then we need to do okay, so then let viewing index equals cycle minus 1 mod 40. And so let pixel lit pixels a pound sign equals if cpu.x int.abs of cpu.x minus viewing index lit equals that is less than 2 in part 2 chars pixel equals if lit then else in pixel pixel part 2 chars oh string of car list dot reverse part 2 Did it work? Nope. Index out of bounds. If t instruction index is less than array length, then else. Naming cycles. Okay. Get an extra new line in there. actually just do this. So our answer is that's wrong. Oh, this should go after. R B P A R A G F. Woohoo! There's the output. Okay. Yeah, so here's our input. I start by parsing the input. I come up with this. There's this instruction struct or variant that is either a no-op or an addx of int. And then we have cycles. This is how long each instruction takes to occur. So I just check to parse the input. If the string is equal to noop, then it's a no-op instruction. Otherwise, I scanf the delta out of it and create an addx instruction. And then I create a CPU which has a list of instructions, an array of instructions, a instruction index. I'm guessing, seems like something. I wouldn't be surprised if we expand the functionality of the CPU in later days. So this seems like a decent start. Store the instructions as an array because we'll probably be jumping around. And then we have the CPU knows how many cycles it has left in the current instruction. And so when I create it, it's looking at the first instruction, and the remaining cycles is however many cycles that first instruction takes, and the X register is 1. So then when we tick the CPU, we decrement the number of remaining cycles. If that's 0, assert t.remaining cycles is greater than 1. Let's just add that assertion. Decrement the number of remaining cycles. If it's 0, then we need to complete that instruction. So we call complete instruction, which actually does the modifications. We call it with the current instruction index. And then, so we pass in the instruction and then just match on it. Then we increment the instruction index, and then if the instruction index is less than 1, or sorry, if the instruction index is past the end of the array, we just set the remaining cycles to 100,000. Otherwise, we get the next index and see how many cycles that has and set that to remaining cycles. So in part one, we're looking at the value of the register at these certain cycles, and we want to add up the product of the cycle times the value of the register at those points. So how does list.range? What is list.range? Start inclusive stop x inclusive oops. So we loop through on the cycles. This is during this cycle, is before we actually run the tick. So at the very end, we tick the CPU at the end of the cycle. And all of this represents the state during the cycle. So we check if the cycle's in our list of key cycles, then we update our part one answer to be add in the cycle times the value of the X register. Part one for part two. For part two, we get the viewing index, which is the cycle -1 mod 40, because we're printing out this thing that's 40 characters wide, and the cycles are 1 indexed, but we want 0 indexed for the viewing index. And then a pixel is lit if the viewing index is within 2 of the, if it's, because it's, what is it called? It puts the sprite. There's a sprite 3 pixels wide. Oops. And so if it's, and that's the middle of the sprite. So if the X is equal to the viewing index, or if the X is 1 to the right or left, then we'll see it. So we just check if the absolute value between the register and the viewing index is less than 2, then it's lit. If it's lit, then the pixel is a £, otherwise it's a dot. We add that to our list of pixels. If we are on a 40th cycle, we add a new line. And then because this gives us, we're always appending to the front of the array of the list. And so at the end, we want to reverse the characters, create a string out of them, and then print them out. Oops, I never stopped my timer. But yeah, that prints out this thing here, which is cool. Yeah, so that is day 10.